Hi there, this is Estelle Trengove and this is my lecture for LN 2017 on Thevenin and Norton's theorems. Before we can look at Thevenin and Norton's theorems, we first have to understand real voltage sources and how to model them, and real current sources and how to model them, and source transformations. To make each video a little bit shorter, I'm going to do real voltage sources and real current sources and their models on this video, and then on part 2 we'll look at source transformations and Thevenin and Norton's theorems. So far in this course we've been looking at ideal voltage sources, and you'll remember that we said that the way an ideal voltage source works is that we see the same voltage irrespective of the load that's connected to it. So if we look at the load voltage VL plotted against the load current IL, then it doesn't matter what we connect to it, how much load current it draws, it will still give us the same voltage. So this graph represents an ideal source connected to a load, and the current flowing from the source to the load is IL, and the voltage drop across the load is VL. With a real source, though, the more load current the load draws, the less voltage appears across the load. And let's call this voltage difference delta V. So this is an ideal voltage source, and this is what we see with a real voltage source. So you can see the voltage is the greatest over here when the load is the smallest. So the best case scenario is when the load current is 0, and that would be an open circuit. So we're going to have the source, and that is going to be V open circuit, and the current IL is going to be 0 amps because of the open circuit. So that's what we see happening here on this line. So we know that for a real source, the best case scenario is when the load voltage is V open circuit. So if you look at the difference between the load voltage for an ideal voltage source and the straight line for a real voltage source, then you can see that the difference delta V is proportional to the load current. So it's proportional to IL, and the constant of proportionality from Ohm's law has the units of resistance, and so we're going to call that resistance, the source resistance, RS. And you can see that we can write the equation for a real voltage source. We can write that the load voltage VL is equal to V open circuit minus ILRS. And so this is the open source voltage, which is what an ideal source looks like. And this is that delta V in our little graph. So we can model a real voltage source as an ideal voltage source with voltage V open circuit connected in series with a source resistance RS. And then we've got a load RL. And this is our load current IL and our load voltage VL. And this part represents the real voltage source. So you can see two things. The first thing is that for RS much smaller than RL, the voltage source, the real voltage source, behaves quite a lot like an ideal voltage source. And the second thing that you can see is if you short circuit the real source, which you mustn't do, so don't do that, because it can damage the voltage source, but then it means that RL is equal to 0, and then we have our source, which looks like an ideal voltage source with voltage V open circuit. We've got our source resistance RS, and we're short-circuiting it now. So what's flowing here is I short circuit. Then you can see that by Ohm's law, these quantities are related to each other by the equation V open circuit is equal to I short circuit RS. And this is an important relationship because it becomes important later on when we look at source transformations and at Thevenin and Norton's theorems. The situation with real current sources is very similar. So remember, we looked at ideal current sources, and for an ideal current source, we said that the load current, IL, if we plot it against the load voltage, VL, then it doesn't matter what we connect to the ideal source, it's always going to produce the same current. And remember, we drew it like this. But again, we see that for a real current source, there's a straight line relationship, and the more the voltage drop across the load increases, the smaller the load current. So like before, this is the curve for an ideal current source. And this is the curve for a real current source. And let's call the difference between the two delta IL. And if you look at this graph here, you can see that the ideal scenario is when the load voltage is 0. So that would approximate a short circuit. So if we have a real current source and it's connected to a load, and we've got a voltage VL across it, then for the maximum current to appear across the terminals, we would have to short circuit it. So we would draw it like this. We'd have a real current source so the load RL is equal to 0, and therefore VL is equal to 0. And then this current here, IL, is going to be equal to the short circuit current I short circuit. So we can see here that the best case scenario for a real circuit is when the IS is equal to I short circuit and the voltage is 0. We can also see from our little graph that delta IL is proportional to VL. And this time the constant of proportionality is the inverse of ohms. So it is 1 upon RP. And so we can see that delta IL is equal to VL over RP, and the load current can be written as the equation IL is equal to the short circuit current minus VL over RP. And again, this is the ideal voltage source. I mean current source. And this is delta IL. And it means that we can represent a real current source as an ideal current source producing current I short circuit connected in parallel with a source resistor, and that's connected to a load RL. So we've got IL flowing here, and we've got the voltage VL across the load. And also you can see that if we open circuit, so this is the real source, the real current source, And if we open circuit that real current source, so we've got I short circuit, and we've got the parallel RP, the source resistance, and we open circuit it, then we can see that all the current from the ideal current source is going to flow through the load resistance, and so the voltage current relationship can be written as V open circuit equal to I short circuit times the parallel resistance RP, the ideal current source resistance. That's everything for this video, so I'll continue with this on part 2.